Hello, this is Dr. Hassan with Innovate, and this is lecture number 51, Analysis Using State Graphs or State Tables, of Chapter 8, Analysis of Synchronous Sequential Networks, of the course Digital Logic Design, Digital Systems, or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in Digital Logic Design, however, there are many books. In Chapter 8, we talked in the previous lecture about models of synchronous sequential networks, namely Mealy, Moore, Medvedev, mixed Mealy Moore model, and we discussed which is the best model to use. Today we'll talk about the analysis of sequential networks using state graphs or tables. Then we have 3 more lectures, one on the analysis of sequential networks by signal tracing, analysis of sequential network by deriving the state graph, and DHDL Design 7. The procedure to analyze a synchronous sequential network or finite state machine using state graph or state table is as follows. 1. From the given input sequence and the state graph or state table, determine the sequence of states and the sequence of outputs. Note that whenever a time sequence of symbols is given, it is assumed to occur from left to right. Assign a binary code to each state and state variable to each flip-flop of the network. Note that n flip-flops are required for a network with capital N states, where the small n is the smallest number, which 2 to the power n greater equal to capital N. So for the 3 flip-flops, we have the maximum number of states is 8. This is what it means. Draw a timing diagram showing clock and the given input sequence. Assume an initial state of the flip-flops or the flip-flop reset to 0 unless otherwise specified. On the timing diagram, we derive the waveforms of the flip-flop states and the outputs by transitioning through the state graph upon each active edge of the clock input. Now, we'll take examples. The first example on Mealy Network. We would like to determine the output response of the Mealy sequential network shown to the input x011010, assuming that the circuit initial in state A and the state changes on high to low transitions or the trailing edge of the clock. Now from the state graph we have 3 states, A, B, and C. And the next state, if I am in state A, the next state will be B if x is 0, or C if x is 1. And the output depends on x as well as the state. So the output, the present output, will be 1 when x is 0 and 0 when x is 1. So if I'm in state A from the graph, from the state graph, and the input is 0, I will go to state B and the output is 1, and the output is 1. If I'm in state B, now I'm in state B and the input is 1, I will go to state A and the output is 1. And if I'm in A and the input is 1, I will go to state C and the output is 0. Okay, and so on and so forth. So I will complete the sequence and I will find the corresponding output and the corresponding for each corresponding input. So we can generate a table as we will see it shortly. So let's look at the literature a bit. At time 0 for the first clock pulse, the input x is 0 is applied. The present state at the present state A, from the state graph, one can read that Z is 1 and the next state will be B. At time 1, the second clock pulse, the input x is 1 is applied and the present state is B. From the state graph, one can read that Z will be 1 and the next state will be A. And continuing with the remaining bits of the input sequence, the Mealy will behave as follows. Okay, at time 0, I am in state A. I go to state B for if the input is 0 and the output will be 1. Now I'm in state B at time 1. My present state will be B. Okay, if the input is 1 the output will be 1, I will go to state A, and so on and so forth. So we finish the sequence, the input sequence, which is 0, the given input sequence is 0, 1, 1, 0, 1, 0, and we obtain the next state BAC, ACA, and the assumed output Z will be 1, 1, 0, 0, 0, 0. However, if you look, actually, the Mealy network, the output not only depends on the present state, it depends on the present state and depends also on the input X. Therefore, Z changes with the state and changes with the value of X. And this may cause us a big problem, as we shall see. So this is what will happen. So if I put actually a number of clock pulses, and we know that the negative edge, those are negative edge triggered flip-flop or the trailing edge. Okay, so the state changes at each of the clock pulse. Initially I'm in A at time 0, the input is 0, the output is 1. Now at time 1, the clock changed, but X is not available yet. So Z will change accordingly, 1 will go back to 0, until X will occur to 1. Once X occurs, Z will go back to 1 because the output will be 1 when X is 1. So what will happen, this generated really a glitch, So if I'm in state, now if I'm in state B, the next state will be A, the input is still 1, okay, still 1, so the output will remain 0, the output 0, again, here X changed from 0 to 1, but the clock occurred first. So there is a glitch from 0 to 1, okay, in Z. Then when the clock, when the X occurred, Z will go back to 0, to what it should be, to 0. It should be the output 0. Then X continued here at the state. The output will continue to be 0 when X is 0. So when X is changed 0, when X changes state and change 0, so you'll see a 0. So this will continue until the next cycle of the state, which is A, will go back to 1, and the graph will repeat itself. Now, so clearly here, so if we examine the output Z in the state table B at time 0, the first clock X0 is applied, and the state A, and hence Z is 1. So hence Z is 1. At the falling edge, or the trailing edge of the clock, the first clock pulse, the next state will be B. From the second row of the state table, Z will drop to 0. Z will drop to 0. Since Z determined, this will generate a clock until the next bit of the input X sequence is applied, which is X is 1, during the second clock pulse, and the hence Z will change back to 1, as it should be. So this is how the glitch is generated, because Z is dependent on X and dependent on the clock as well, because dependent on the state. Continue with the remaining bits of the sequence. Z will be 1, between parentheses 0, 1, 0, 0, between parentheses 1, 0, 0, where the values in the parentheses represent the false output or outputs or glitches. The two glitches occur since the output Z can change at any time the input or the state changes, since Z is a function of both. For this reason, Mealy network has a really considered to be a drawback or disadvantage because of these glitches, especially when we are dealing with very high frequency application. Now, the remedy for these glitches is Moore network, because in Moore network, the output Z dependent only on the state. So Z will occur at the trailing edge or the negative edge of the clock or the positive edge of the clock. It depends on the type of flip-flops used. So in this actually example, we will consider Moore network, and we would like to see the output Z when the input is 0, 1, 1, 0, 1, 0, assuming all the state changes occurring at the high to low or trailing edge of the clock. Again, we have 3 states in the state graph, A, B, and C. When I am in A, the output is 0. When I am in B, the output is 1. When I am in C, the output is 0. And when I am in A and the input is 1, the next state will be B. If I am in A and the input is 0, the next state will be C. Okay, and so on and so forth. And with this table, we can test for the input, given input to us, which is 0, 1, 1, 0, 1, 0. So if we follow the state graph or the state table, at time 0, we are in state A. The output will be 0. The next state will be C. If I am in C in the next time interval, the output will be 0, for the input is 1, and the next state will be A. Now I am in A. For the input is 1, the output is 0, and the next state will be B. Now in state B, and so on and so forth. Okay, now also if we look at the timing diagram, the timing diagram will be free of any glitches, because as the input occurs between the pulses, Z is dependent on the state. So Z0 will remain 0, of course, here, okay, with at the negative edge or the trailing edge of the clock. It will remain again 0 because the output will remain 0 at the other edge of the clock. Then we'll switch to 1 at the third edge of the clock. Okay, then at the fourth edge of the clock will remain 1, then switch to 0. Okay, so Z depends on the clock, that does not depend on X at all. Okay, and accordingly, the output Z will be free of any glitches in the Moore network. And this is a great advantage of the Moore network over the Mealy network. Okay, and this will be the end of this lecture. I thank you so much for listening. Please subscribe. Hopefully to see you very soon in the next lecture. Sincerely, Dr. Hassan.